In this video, we're going to look at collision theory of chemical reactions. According to collision theory, the rate or speed of a reaction is proportional to three things. 1. The number of collisions per second. 2. How often the orientation of the molecules is correct. And 3. What percent of the molecules have sufficient energy. Next, let's look at each one of these three requirements one at a time to understand the molecular origin of them. Let's look at the reaction A plus B is transformed into products to investigate how the speed of a chemical reaction is proportional to the number of collisions per second. Here we have two scenarios. Scenario 1, where there are 3 molecules of A and 3 molecules of B, and scenario 2, where there are 6 molecules of A and 3 molecules of B. In order for the chemical reaction to occur, the reactants A and B must collide with each other. We can see in scenario 1 that this B molecule could easily collide with that A molecule, resulting in a chemical reaction. In scenario 2, because we've increased the concentration of A, this B molecule could now collide with that A, or that A, thus increasing the number of collisions per second that are possible. In fact, the concentration A was doubled in scenario 2, therefore the number of collisions per second will also double. The number of collisions per second is directly proportional to the concentration of the molecules. Let's look at the reaction between nitrosyl chloride and the chlorine atom to investigate how the rate of a reaction is proportional to how often the orientation of the molecules is correct. First, I'm going to draw a kind of cartoon or reaction scheme of a successful collision. Before the collision, we have the chlorine atom and the nitrosyl chloride in this particular orientation. These arrows represent the vectors or their motion as they're coming together. Here I've drawn the actual collision where the two chlorine atoms are actually touching each other. And in this final state, this is after the collision. So a bond has been formed between the two chlorine atoms, and the bond between the chlorine atom and the nitrogen atom has been broken, and the two species are now drifting away as indicated by these arrows. Now let's look at an unsuccessful collision. Here I've drawn the reaction scheme again, the kind of cartoon showing the two reactants, but notice I've flipped the orientation of the nitrosyl chloride. Here's the collision between the two reactants. Notice that here the chlorine atom is actually touching an oxygen atom. Because those two atoms are touching each other, this collision is unable to form that chloride-chloride bond and unable to break that chloride-nitrogen bond to result in a successful collision or a successful reaction. After the collision occurs, the two unreacted reactants simply drift away from each other. The rate of a chemical reaction is also proportional to what percent of the molecules have sufficient energy. What I mean by that is what percent of the molecules have enough energy to break the chemical bonds that already exist in the reactants. As we saw in the previous slide, in order for a chemical reaction to occur, bonds in the reactant molecules need to be broken. The way I like to think about this is Red Rover, the game where a bunch of people line up as drawn here, and then one person runs and tries to break between two people and break their where their hands are held together. In order for a chemical reaction to happen, the reactants have to have enough energy to break the existing bonds in the reagents. In this example, the energy the person running has is in the form of kinetic energy. We would calculate their kinetic energy using E equals 1/2 mv squared, where m is their mass and v is their velocity. We can think about the kinetic energy reactant molecules have based on kinetic molecular theory for gases. Here's a plot showing the number of molecules as a function of their speed, or we could think about that as velocity in units of meters per second. Notice that not all of the molecules have the same speed. There's in fact a distribution of speeds for any collection of gas molecules. As we increase the temperature, the distribution shifts further to higher speeds. That is, if you increase the temperature, the gas molecules are actually moving faster. Let's return to our definition of kinetic energy, where kinetic energy was 1/2 mv squared. Notice that as we would increase the temperature, we are increasing the speed, or let's say velocity of the molecules in this case. Therefore, increasing the temperature is actually increasing the kinetic energy. What this means is that as you increase the temperature, you are increasing the average kinetic energy of the molecules. As you increase their average kinetic energy, the percent of molecules with sufficient energy to make the reaction occur increases. Thus, increasing the temperature also increases the rate at which the reaction occurs. The way we express this in chemistry is that kinetic energy is equal to 1/2 mv squared. It is also equal to 1/2 RT, where R is the gas constant and T is the temperature in Kelvin. In conclusion, the rate of a chemical reaction is proportional to three things: the number of collisions per second, how often the orientation of the molecules is correct, and what percent of the molecules have sufficient energy to break the bonds in the reactant molecules.